yeah, my name is Christoph. I'm from Simulate, and I guess we chatted about this just there, but we're basically discrete event simulation software. And I'm a consultant there, so more on the technical side. I have nothing to do with like sales or marketing, just really more training people in the software, teaching them how to use it, but also building projects. Like people give us data, we build a simulation for them, whereas most simulations will be more like process-based, so patient flow in a hospital or how something gets produced in a manufacturing line and that kind of stuff. So this talk is somewhat with a non-standard, so idea of how we use data, I guess, to run simulation more for sort of an operational use. So essentially what you can get is you can get simulations that are built for a one-off question where someone says, I want to increase my production capacity by X%. Don't know how many more tanks do I need in a distillery plant or something like this. And then you basically just build the simulation, get some results, and at the end someone is hopefully confident to make a decision. So this is actually more about the sort of context where we are interested in making decisions more regularly, like even daily or something like this. And in this context, what we, and I guess sort of a lot of the simulation community have been more interested in, also given possibilities, is somehow getting live data of some sort. As I say, it could be that in the morning you check your live data as a hospital, see which beds are currently full, and then try to predict or run a simulation forward to see how the day might turn out if certain assumptions apply, like the day goes on, like length of stay and stuff like this goes on as it has been, and then make decisions to somehow avoid maybe some bottlenecks. Maybe you can release some patients earlier if you see, if I don't do this, I end up with like a full ward. Well, in this talk I want to talk about using machine learning. It's more like an experimental idea, but there is some literature which I'm going to briefly just cover, give you an idea of what sort of has been done, but basically just an idea of how we can improve the arrivals. So traditionally, in a discrete event simulation context, you might define your inter-arrival distribution and say, like, I don't know, a part comes in every 10 minutes. So and this is actually inspired by a project we did in defense, and it was for maintenance. So basically they had, well, I explain this in a second in more detail, I have it on the slide, but essentially they had the case of they produce radars or radar systems. They will be given to, say, an Air Force, that's their customer, but at some point they need to contractually make sure that if it breaks down and has a failure, that they can somehow give them another radar that is there, or that they can also get the repair somehow done quickly enough so that basically they don't end up having to wait, because without the radar they might not be able to fly and have to stay on the ground or something. But before I go into all this with the case study, as you might imagine, machine learning is playing sort of an ever-growing role in also discrete event simulation, or just any kind of simulation, to be honest. And also the idea of using live data with it, so feeding it into a machine learning model and then making maybe some prediction to be more accurate than sort of fitting a historical distribution, which I've nothing against. As I say, I think it really depends on the context, but yeah, it's really the decisions you want to solve and what data you have and so on. And I think just really try to give a summary. There might be 3 different ways that we might use machine learning. So one is, as I say, and what's mostly the topic of this talk, is looking at getting a better prediction for arrivals. So if you're thinking about either being in a hospital in the morning, a shift starts, or even have a production plan or your maintenance plan, you might want to know what comes in during the day. As I say, the traditional way would be have some sort of rate of how often customers, etc. come in, but you might also be able to say, given certain factors that I can feed into machine learning models, can it tell me how many people I might expect today, or parts or something, or failures. Then the second sort of way, or way we could use machine learning is for, again, predicting timing. So I come to the literature in a second. There's a nice example of in a manufacturing plant, you have a certain process step, but you can imagine that if I need to produce something, or even say recycle, I think it's actually quite interesting in things like where you don't really produce something from scratch, but rather recycle something. A lot of the times, like how long does it take to clean it, polish it, or do anything with it, will probably depend on the condition, maybe on the size, on anything like this. And based on this, rather than just saying, giving a distribution, and saying this might take roughly 20 minutes, plus minus, etc., you might have some idea and say, well, if it's this size, if it's this condition, and so on and so on, I can actually have some sort of, usually like supervised learning idea of what the timing should be. And then the third one, without really having done a too in-depth literature review here, obviously, but I think that the one that's mostly addressed is sort of the routing logic. So again, in sort of the actual traditional software, you will see that you can specify rules where something might go next. Like you can imagine that you have sort of modeling a hospital where after receptions, patients can go two ways, and you can say, well, 20% of patients go up, 80% of patients go down. But again, here it might be something where you could say, given that the patient is that age, has this condition, etc., etc., they maybe are more likely to be routed somewhere else. And that's kind of where machine learning, or supervised learning, I guess I should say in this case, can be more useful. I'm not going to go too much into this, but there's also this reinforcement learning aspect. So instead of doing sort of optimization, I guess, sort of the traditional way, people more and more often try to use a simulation almost like an environment in reinforcement learning. So run this maybe in Python, then the simulation will come back with the feedback of was this decision good or bad, and then it kind of goes until they kind of figure out what's the best sort of decision sequence instead of just from a sort of reinforcement learning point of view. I'm not going to go into this link, but we do have some stuff like help files and stuff. If you're interested, I'm happy to provide you either with the link, or also you can always get in touch and I can give you any kind of help files and stuff. So basically just what I just said, and not really want to bore you with too much literature here, but there is some stuff that has been done where things like things like random forests or decision trees that have been used to. The first one is exactly the example I just said, where they basically have this idea of a manufacturing plant, in this case, sort of putting some industrial powder coating process. And basically what they say, rather than just giving it a distribution, saying this takes 10 minutes, or according to some distribution, 10 minutes plus minus, etc., they basically say, if it has a certain size, is a certain condition, needs cleaning or not, or something, or has some degree of cleanliness or something like this, basically then we can predict the time, how long it takes to actually this specific item, how long it takes, I think in this case, to sort of coat it in powder or something. It's sort of a winters in paper, so it's fairly short, and the case study is just really more like an illustrative case study, but it's still interesting because it tries to take in these factors, how you can then predict the time. The other one is more with the routing aspect. Rather than just using like a first in, first out routing logic, you basically just say, again, based on some factors, I could maybe use some supervised learning to say where it should be routed to. And then, the last one, it's basically like what people try to use, like neural networks, again, based on some patient in a dental clinic, to basically, again, try to predict how long they might take for a procedure or something, rather than using sort of just traditional fitted distribution from some historical data. Do it based on the patients. I would say also that if you basically just go into, say, some Google Scholar or whatever you want and just go into machine learning and simulation, most of this stuff go more in this sort of meta modeling idea, so it's almost like using a simulation to train a machine learning model. So think about, you have a neural network that takes certain inputs, gives you some outputs, and basically they train it by running a simulation, and they basically try to closely replicate the simulation outputs and inputs, and then that basically saves you probably in the end sort of computationally, etc., to just go from not always having to run a complicated simulation or develop it once you have it sort of in a neural network that does that. It might help you in certain contexts to run this instead of the simulation, but it's just a sort of slight difference that I'm mostly talking about, and I guess interested in this applied machine learning within an actual simulation rather than the idea of using the simulation for training or replacing it eventually through machine learning. But I should mention that this is also a case. Then the next slide we actually start with a case study, and hopefully can talk a bit more about an actual application. So we are interested a bit in this sort of looking at especially aircraft, and aviation is probably the closest related to our case, sort of anomaly detection. So basically what we want to look at is, if I have a fleet of aircraft, and I think it's quite related to what was mentioned in Tuesday morning's talk about predictive maintenance, that if I have this fleet, I might always have sensors on those aircraft, and I can somehow try to get some data out of what's their current condition. Do they still have a flight? How many flying hours did they achieve so far? I don't know, are they currently in a country where it's snowing all the time? Basically try to get this data to somehow predict when I need to repair maybe an aircraft for my fleet in that way. Not so much simulation related, but some literature that I'm going to sort of make use of is this idea of when you manage something like a fleet or something of aircraft, how to do predictive maintenance, and as I say, try to figure out these factors that maybe tell you that this aircraft is going to need a repair in 500 hours or something like this. And there's just some sort of context on what has been done in that area. So yeah, basically just talking about this sort of case study where we did this as a project, whereas the machine learning stuff was more just me going off and trying something out that maybe could have been done as well, just more out of curiosity. But basically what we're talking about is sort of a supplier of radar systems. So basically they produce these radars. The typical customers might be some defense companies, or like any sort of coast guards, anyone who does sort of surveillance or something like this, and also some sort of air force that might need do surveillance and things like this. So basically they put sort of an aircraft on a radar on a helicopter or on an aircraft, and basically what their problem was that they were interested in modeling or simulating the process of the maintenance sort of system, but they were mostly concerned with that you need to make contractual agreements, as I said earlier, where you say, well, if one of our radar systems fails, then you send it to us, we can repair it, but obviously the customer, like an Air Force, is not going to sit there and say, yeah, you go off, you repair it, and maybe in I don't know how many days you're going to give it back to us. They obviously want to go right back on and keep flying. So you either need to make sure that you have a spare part ready that they can directly replace, and then I guess you don't have to worry too much about the actual sort of radar that has to be repaired. Or you basically have to somehow make sure that the repair is happening fast enough for them so that they don't obviously turn around and complain to you that it's taking too long to go back into the air again. And obviously, I guess the obvious solution is that you don't just have these radar systems. If they're in the millions of pounds, you don't just have a warehouse where you can quickly replace one another. So you obviously want to minimize this as much as possible, so that you don't have just spare parts that maybe hang around and are worth millions of pounds. And that was basically the overall project, that we wanted to just simulate this repair process. And we then played around with sort of some historical schedules, like what was the historical data on how often repairs came in, but also just sort of standard distributions, and just try it out and see how the system can cope with this if there's bottlenecks and so on. So just sort of a screenshot, but basically you have things coming in, and then so it's kind of this arrow pointing this way, and then all these boxes are sort of different steps in the process. So it can be something needs a certain test, like you repair it and then you need someone come and test it. But there's other things where maybe, it's not as simple as that, but where you make it tighten a screw or something. You can imagine how this is a process, and they're not linked. So I don't know if quite often if you have the discrete event simulation, it's quite sort of you have like even a process map sometimes, and you just have it linked and it goes to next. Well, here we have done, because it was more complex with the routing, we almost did it like a matrix where you say, if you're a specific item, you have to look up where you go next. So rather than linking it, there is basically some code sitting at the last of these where it always looks up where I currently have been and where I go next, just because it kept it more flexible than having actual sort of links drawn out. Well, that's just sort of technical detail. And then, basically coming now to the main thing for why something like, I guess in this case, supervised learning could be interesting for this is that, similar to having a commercial airline where you might have a fleet and they fly around the world, and you kind of want to know when they might come in for repair. Obviously those sort of radar systems, etc., are also going to have something like a remaining useful life, which you might want to model. You kind of want to have some idea of, I don't know, have in a simplified way 10 radars out there somewhere with customers that can be all over the world. And I kind of want to know, actually, is one of them coming to the end of its life? And once it does, there's again also quite complicated processes can happen, but they might have then to come back to the UK to either be repaired, or they have other sort of places around the world where they might do that. So basically the idea is then here to just play around with ideas of how we can use something like, in this case, they say a convolutional neural network to try to figure out different settings of this to somehow model this remaining useful life, which then feeds into the simulation. And then in a sort of ideal world, you would then also have you do have the live data, but in an ideal world it works that you can just plug it in. It sort of spits out your remaining useful life. And the idea is that just the way that it connects to the simulation is that once I'm below a certain threshold, you can get this sort of survival idea or survival plot of how likely it is that I actually need a repair. So it's basically like a car. Once I have this sort of remaining useful life and it tells me I've only 100 days left, then it doesn't necessarily mean that exactly in 100 days I'm going to need to have it repaired. Maybe it needs a 50 days, but it's still less likely. And it's basically this idea of once we're in this certain region at the end of the life, the sort of probability goes up. And that can then go basically in this start point instead of saying as using like a static schedule. So basically, and we want to sort of play around with different settings for a convolutional neural network. And also, just to make it clear, the difference, I guess, to commercial aircraft is that obviously with something like a Coast Guard, Air Force, and those kind of clients, obviously by all means, commercial aircraft or aviation is obviously quite challenging by itself, but with sort of Coast Guards, I guess, and Air Force and stuff, you might even be in more extreme conditions. So we are basically talking about having customers all over the world, so that some of your systems might be somewhere in a desert, region and some are somewhere in snow. And if you think about something like a Norwegian Coast Guard where the radar system is just sitting under a helicopter, if they land in snow, then you don't really know what kind of impact it has, and you try to somehow, again, see if something like weather and so on has an impact. So, yeah, the idea and then the hope is that I'll show you a bit more about the data set in a second. But basically, you can have these different factors, essentially, of what your radar systems are currently doing. And some of them might be relevant to try to get as much, say, live data, so as most recently updated as possible, whereas other ones are probably not changing too much. So examples are things like, sort of in the sensor sense, you can have the current condition, which is very much like this sort of aviation industry, where you have some sensors that maybe say if a part is in a certain condition, sort of degrading quickly or not. The current location, again, maybe if you're somewhere in Canada or something, you might go from a very snowy environment a bit further south where you don't really have snow, and kind of vice versa, and those kind of things. So you're trying to find out if I can get like an updated data set of where they're currently at. Does this maybe tell me that they've now been in snow for a week, and that maybe tells me that they're more likely to fail and this remaining useful life goes down. And things like an installed platform, like whether it's under the wing or under the body or something, is probably not too much of relevance, given that that doesn't really change. And then also other things like weather, and also things like the flying hours. So I guess with something like a Air Force or something, what you might sometimes see is they obviously not just use their aircrafts when they're sort of in combat, they might also do training sessions much more frequently. And then if you want to look at sort of the cumulative flying hours, how much they have flown in the past week, year, etc., then obviously that might depend on these things like, which you don't really know when you see it from the outside as a manufacturer, of maybe they cancel the training session because some pilot was ill, so the aircraft is just standing around for a week, or obviously they just fly as much as they can because they have some new trainees that are now allowed to fly and they're really keen. So again, it could be quite useful to have this most recent data or live data of how many flying hours have we actually accumulated. And then the idea is that you can have this sort of data set which you can then use. I should mention sort of this was, I looked at this paper which didn't do it in a simulation context, or it didn't do it in a live data context, but it was more on estimating remaining useful life using those deep convolutional networks. But essentially what you get is almost like a table that looks a bit like a time series format. So you have something like the ID, so if it's your radar 1 or 2 or 3, so you know which one it is. You have certain timestamps, and then those features refer to like the previous slide where you can say this was the amount of flying hours we did, this was the weather conditions, this is where the current location is, and all these kind of things. And obviously the sensor data of sort of conditions of certain subparts. And then the outcome, which you basically here have as a predictor, is your remaining useful life. And then what you have is you have these sort of data sets that have this whole end of life for each radar. And what you can then do is basically try to fit for certain radar systems. So I didn't mention this actually, but in the previous case we had, say, 4 different type of radars. Some are sort of a bit smaller, more sensitive, some are a bit bigger, can do different things and so on. So you obviously have different product types essentially. And you have those data sets which are basically time series in a table format for this end of life information that then goes into predicting this remaining useful life. It's just sort of some stuff about sort of data points, but then basically, there's sort of these sort of steps, and hope it's not too boring, but basically we looked at Removing sort of any features that didn't have any variance. So if you have something that obviously doesn't really change, then you might want to remove it from your data set to not introduce any sort of features that are not relevant. Things like normalize the training predictors, and also then with the data format it comes in, because it's basically this sort of table of time steps. You might have some that have failed after 100 days, some after 500 days. So there's sort of some technical aspects of basically bringing it into the same sort of batches. I think we call it like padding, for instance. Yeah, and then it's basically just, we tried out sort of the different factors here, different sort of activation functions, those kind of stuff, and then we basically came up with a sort of convolutional network that actually worked. So that's sort of the usual. We took like 20% of the data for validation, trained it up, tested it then with the data that we haven't trained it on before, and we sort of came to the conclusion that generally that seems an interesting approach. And as I say, it's not sort of just us doing it for the first time. There is sort of a lot of interesting maintenance and aviation studies out there that basically have the same goal. They might call it something differently, they might not connect it to simulation, but they're basically also trying to find anomalies based on any sort of features of some fleet, or it could obviously have some other kind of fleet. We then sort of stopped the training just also to avoid any sort of overfitting. And just if you're interested in, obviously I can talk about it as well, but we basically use Python sort of for the technical side, those packages, TensorFlow, Keras. Basically had that connected, that you had Python connected to simulate, and then back into Python, so it's this kind of looped environment, and use that with like something like COM, where you don't even need to open simulate, you basically just do Python, simulate Python, and don't really need to worry about the simulation running in the background. And I guess overall we kind of concluded that this worked quite well. It's interesting, I guess, as well, especially because in this case we could see that the data was available to some extent for sort of most systems. However, there is also quite a few drawbacks also related to the applicability for like live data. So there's first of all, I guess, the human factor, which is we've figured out that a lot of stuff had to be manually inputted. So sometimes, if you're in this case, depending on where you were, you actually had to have engineers who had to manually input a current condition into a sort of SAP system, but they might do that at the end of the day, like they're not going to sort of just stop having their lunch break or something, or stop working. They might just do it at the end of the day or forget about it, and then you get a data set that is sort of the live data, latest version, but maybe someone sort of made an error, so there's also these things. In this case it was also challenging, I guess, globally, that again you had all these different conditions, like some of these systems are somewhere fitted to a helicopter that's somewhere in a desert region, some in a sort of snowy region. And again, you don't really get the sort of most up-to-date data with this. And then also, there's also a lot of like confidentiality when it comes to defense industry or defense customers. They might not even give you the whole data set, or again, only after several rounds of sanitizing it, etc. Then the other thing, I guess, is which is more like from me as a simulation consultant point of view, is if I then have to explain this, why the simulation runs, and currently there's sort of, I predict like that there's going to be 100 failures or 100 repairs needed that come into this system. Obviously, someone who has to then use it, who is an analyst in a company, will ask, why is that happening? And then there's maybe some sort of familiarity with it. First of all, why did you choose this machine learning method over another? There's this whole thing about how do you explain this to people. which also is sort of a limitation of this one. I could have probably played around with other sort of models and tried out if something else is better. And then the whole thing, which I guess has come up quite a few times at this conference anyway, with like sort of a lack of explainability of some of the results and so on, and you need sort of explainable machine learning and stuff for actually getting this through to people so that they understand if I have my arrivals coming into the simulation, where does this number actually come from? And then, yeah, I guess I kind of mentioned stuff. It was interesting anyways to try this out as an alternative to the sort of standard thing in discrete event simulation where it might say we use inter-arrival times for the arrivals. It would be interesting to obviously do this for the other sort of areas that I mentioned at the beginning, which is like predicting timing of a certain activity, again based on maybe size of something, or I think even more interesting in a hospital context where you can say if the patient is a certain age, if they maybe have a certain condition, if they have already been in treatment for 100 days, etc. Is it going to be likely that their length of stay in a bed is longer than someone else? So there's definitely, I think, quite interesting things that can be done with it. As I say, have sort of appeared in the last years anyway, but probably much more can be done, especially with the sort of explainable machine learning and stuff, just for, again, if you have a hospital analyst, I might want to know why I'm currently saying this guy has a length of stay of 100 days, whereas my historical data might tell me they have 200 days. Yeah, and then the rest is obviously with the sort of connecting it to live data, which I've mentioned previously, is just the whole idea of, I mean, the sensors and stuff, especially in aviation, that's quite nice. You get the sort of most up-to-date, it's all automated, but I think in this case it kind of shows as well that a lot of stuff is still manual by trying to get engineers to actually check the condition, that kind of stuff. Or just even get current locations can sometimes be tricky if maybe an Air Force doesn't want to tell you where they're currently using this. So, yeah, thanks for the... Yeah, you can clap if you want.
Thank you very much for that presentation.
Yeah, sure. So there's different questions.
Yeah. Sorry I missed the beginning. I was interested in, I know a tiny bit about this, but simulate, can that use live data? Or, you know, is it data that you've manually put in or periodically loaded? How does that work?
Yeah, so we do use live data, so basically, I mean, I showed this yesterday. Maybe it's too much hassle to do that now, but I could show you as well. Basically, usually how I show it to people is like, I have a simulation where I basically click a button and then it runs an R script that goes to the Met Office website, takes the latest meteorological data, like in temperature, and feeds this into the simulation. That's usually how I sort of show it, but yeah, I mean, it's the whole setup of, so Simulate will have things like log files or something, which are just sort of the internal spreadsheets, and we have done it with like in healthcare and stuff as well, with like the latest which beds are currently occupied and which are not. So it does this live data element, but I think it goes more back to how our clients sort of do it themselves in terms of where does the data come from.
Okay.
I think sort of getting it into Simulate is the easy part, I guess. But
Can I ask a quick clarifying question? When you say live data, what frequency of live inputs are you looking at?
Well, that was my question really. So, I mean,
oh yeah, I mean,
is it really live or periodically you've got an interface with...
Yeah, I would say.
Yeah,
you get more. It's more like this sort of making daily decisions,
okay.
And someone starts a shift. They try to get the latest data, run forward what the data is going to
automatically load it.
Yeah, exactly. I mean, that's the.
I have a question about whether there are any thresholds or how the performance degrades with a lower quality or lower volume data. So,
Yeah, so
anything like
I mean, it's definitely a good point. I mean, we definitely had certain, I don't think I mentioned it, but basically had certain regions where it just didn't make sense, where the data quality was too poor. Because basically think of having sort of different radars in different parts of the world, because that's where the sort of customers are. You definitely get sort of some regions where you just don't get good data quality and so on. I mean, I don't really have this sort of threshold where you can say I need to have up to that many rows in order to make it work. Yeah, that's definitely something I would have to sort of more investigate and stuff like this. But it's definitely a point where you need to.
I mean, I know data is ubiquitous, but there are also many applications where the data isn't good quality, or actually it's sparse in time, or sparse in coverage, and those are really interesting areas to look at.
Yeah, no, exactly, and this is so one of these drawbacks and stuff, especially if you do any sort of, I guess, just generally, I guess, of this fleet management, where you're monitoring a fleet and if a part or asset in the fleet is going to come in for repair, especially if you globally do it, whether it's commercial aircraft or any other sort of, yeah, I guess you're definitely going to have certain areas and stuff where, like if it's not automated, you need an engineer that basically has to tick a box or put it into an SAP system, then yeah, you probably get data quality or missing values, all that kind of stuff. Yeah, sure.
I've got two questions. The first one is
Yep.
pretty stupid. You showed your mean square error results. And clearly it was improving, that's good. What sort of mean squared error value is your client happy to accept?
I mean, this was, as I say, more experimentally, so it was more for me seeing if it worked. It wasn't. I mean, we did sort of discuss it with them briefly in terms of, yeah, it's something that we're interested in, but we kind of went forward with this sort of more traditional. But yeah, I guess that's a good point. I mean, I guess especially in a sort of, if you're working with a client, etc., they would have to.
Quite often doing that,
Yeah.
you dictate the size of data set you need to get.
Well, yeah.
they're looking for. The second question, you mentioned that your data set, you had a data set with 15 features for every point.
Yeah.
Did you have a look at which features were the predominant ones, the ones that your model ended up weighing the highest, and then extrapolating from that, which aspect of the system setup has the largest impact on failure?
Yeah, no, so I'm aware of these, like, I know something called this sort of Boruta method. It kind of gives you the feature weights of which ones might be more predictive than others.
Yeah.
No, here we didn't really do it. We just sort of did a very simple thing where you analyze the data, and as I say, if something didn't really change, because there was this sort of time series format, you would say, probably not relevant here, but yeah, I get what you mean. There's the sort of, the sort of Boruta thing, I think is one of the methods that you can use to get this sort of how much prediction stuff you can have.
Thank you again.
Yeah.
Okay, so I am Chris Davis. I'm, as mentioned there, a local lad to Bangor. So I am now happily working in my own hometown, university. That's it there. Excellent. Okay, so the session for today that I'm going to do a presentation on is partly based on work that I did for my PhD. It was a CAS2 funded project, and it involved a local company that are based down the road in Vellinhelly, and they produce frozen food and things of that nature for a whole range of industries and businesses. They tend to supply wholesalers, so and then obviously that ends up in pubs and things like that. So the brief was And I'll go through the agenda first. Is I'll give a brief introduction to what it was all about. And then I will go through some past approaches in determining how to make the decision between make to order or make to stock. We'll run through what those things mean in a moment as well. And then I will go through the process that we developed with the company themselves, and then how it ended up behaving in terms of some data that we had based on their actual demands for the products that they had there. And then from there, then future work to be done, because obviously I'm completing it to turn it into a paper, so I've got a few extra bits and pieces to add on to it as well. Okay, so Frozen Local Food Company got in touch with the university to scope out doing a KTP initially, but then that turned into doing a PhD on the back of it. And the idea was to help them move from what was mostly a make-to-order environment, which is quite classic in most sort of food manufacturing sectors. But they wanted to kind of smooth their production because they were running in fits and starts, as you can understand with it being made to order and things like that. They had a limited range of products that were made to stock, but that was at the request of the customer themselves. So they knew exactly how much they needed to produce for each month for that particular customer. But they were interested in having more of their products made to stock so that they could then fit that into their production schedule to kind of level things out and make things a bit more normal in that regard, and maybe as well start building up stocks over, say, the late autumn so that they're ready for Christmas, which was one of their big busy periods, as you can imagine. So they needed a method to basically make that selection between how to treat each individual product. They wanted it to be pretty straightforward as well, so they didn't want anything that was mathematically too complicated or anything like that, because they just wanted something that their particular production planners and things like that could utilise and understand without it being too complicated for them, because none of them had any particular training or anything like that. It was a classic example of a family-run business. People got taken on and employed, and then they moved through the ranks and eventually became a production planner and things like that. So they're very much based on the experiences that they gained whilst they were in the company, rather than having any formal training in that regard. So as I was saying, they initially ran mostly on make to order. They didn't have any analytics or anything of that nature, surprisingly. The nearest that they got was a monthly meeting where they literally just went over the previous month's sales, and that was about it. So they had no idea of any long-term trends or anything of that nature. So as you can imagine as well, their products would generally have seasonal factors. So obviously anything made with turkey would be a big spike at Christmas, lamb products, a big spike in Easter, and so forth like that. And some of them were quite trendy and other ones weren't necessarily. The lead time on orders was set at about twice the amount of the longest time it took to produce one of their particular products, so they generally managed to meet their orders on time. If they didn't, the customers had an arrangement with them in their contract whereby they could kind of penalise them, so they had that as a driver to make sure that the orders went out on time. So the lead time was roughly about 2 weeks in terms of the orders, and then in terms of the production for the longest product that they made, it would take 5 days to do, because they had like a marinating process involved that took over a whole day. So here's an example of two of the products. As you can see, they're quite random. Some of them, and this kind of led to the impression amongst the staff that realistically you weren't going to be able to forecast any kind of demand or anything like that. But actually, when I did some initial investigations into their time series and things, I did actually find that some of them could be forecasted and reasonably accurately as well in that regard, and that kind of opened their eyes up to the notion of setting up this process of having made to stock and made to order. So I'll just briefly go over this because I'm sure we all know what they are. Make to order is basically a pull system, classic just-in-time processes, so it's basically done whenever the order comes in and then you pull through the production process. Make to stock is obviously the opposite of that. in that it's made to some kind of forecasted amount and then put into storage ready for the customer to pick up. Obviously, there are inventory costs associated with that, which is why we didn't want to go down fully the make-to-stock route. But in terms of storage, because it's frozen, they were able to potentially store their products for up to 2 years in the freezer storage that they had, which was a huge warehouse, big, massive freezer. It's down to about -30 or something like that. So they were able to keep products a reasonable amount of time. So there wasn't the classic kind of perishability issues that you would normally get in food manufacturing, like say if you're dealing with dairy products or something like that. So, obviously, with make-to-order and make-to-stock, there are benefits and disbenefits to either approach, which we all probably know, but having some kind of hybrid approach where you're treating some as make-to-order, some as make-to-stock, that basically means that you can kind of take advantage of both of the approaches and hopefully iron out the disadvantages. So you need some kind of decision process there to kind of help you decide that, and this is what we were working on. So in terms of the literature behind this, some of the earliest work done on discovering hybrid approaches was in 1965 by a chap called Pop, and that kind of fits in with the fact obviously that computing technology is becoming more available academically in that regard, so they were able to run simulations much more effectively than they had done before. And what Pop found out was that basically the hybrid approach tended to outperform make-to-stock on its own, and that as long as the make-to-stock costs were lower than the make-to-order costs, that would tend to outperform just running strictly on a make-to-order approach. After this work by Pop, there was quite a gap. Surprisingly, there wasn't much work done on it in the 1970s, but Williams came up then in 1984 there, where they split products into 4 different categories based on their variability and the average demand, and then basically then you would have a different strategy for each of those categories. Carm in 93 proposed like the ABC classification, so that's like a classic Pareto distribution there, where the top 20% volume sales were going to Group A, and then B and C would be the rest of them, and basically Group A would be treated as make-to-stock, and then B and C as make-to-order. So that was a very simple kind of selection process there. But that doesn't really take into account too much in terms of like how forecastable an object is or something like that, because it may well be that you've got a top volume sales in band A, but they could be quite erratic, they might be intermittent, it's just that over the year they add up to a huge amount. So that kind of system there isn't necessarily picking up on that. And then other studies highlighted the fact that it can get quite complicated based on the individual circumstances. So Ariel and Risa here in Decoy did a paper where they discussed a whole range of scenarios and coming up with some possible solutions to them, and emphasising the complex nature that can sometimes arise, particularly when you've got multiple production lines and things like that, and a good range of product. So it's a pretty complex circumstance there, potentially. Van Donk in 2002, Olhager did similar work as well from 2003, where they introduced this notion called a decoupling point that basically separates the order-driven activities from the forecast-driven activities. So make-to-stock, the decoupling point would be right at the end of the production schedule because they're strictly making to stock, so it's all forecast-driven. Whereas make-to-order, the decoupling point would be quite literally just after maybe buying the raw materials or something like that. And so it gives an idea then of where the difference is between your forecasted activities and your order-driven activities. So moving on, Soman in 2004 proposed a system, and we kind of roughly initially based the original proposal to them on this work, where basically they were determining how to treat the products, and they were using the product's coefficient of variation as a measure of variability, which does have its issues, but then also as well the average demand, well, it's a cut-off point for what would be high and low demand. Both of those decisions are quite arbitrary, so you have to determine what level of COV you want, so determine whether it's too variable or not, and then obviously determining what's high and low in terms of production demand. But we did work on that further. So they moved on to that, and this is in the 2007 paper, this is where they proposed this methodology. And basically that would just literally split products into make to order or make to stock. So for our particular model that I'm presenting here, we do use the MACE measure, and I'll move on into that to describe why we're using that one as a measure, but it's basically being done to incorporate how forecastable a product is, and there's no arbitrary cut-off, and I'll explain this one a little bit in a moment. So, for the forecasting bit, which we do have within this, we use the ETS method as developed by Hindman, which is a state space approach to the ETS family. So that's exponential smoothing. So you've got it's classic exponential smoothing, hots and hot winters. And this is basically a state space formulation of that. And there's a very nice R package that we were able to use in order to do this for it. So all of this will start to make sense once we come through into it. So initially, what we set up was a model where we had a low coefficient of variation, high production level would be made to stock, obviously, because that's nice and predictable, and then a high COV, low production levels, MTO, and then sometimes the high COV with a high production level sometimes might be treated as a made to stock, depending on the production availability that you've got in your production plan over the next month or so. However, what we found was that setting the COV, and of course what is a high-low level of production, was quite arbitrary in nature, and there was no real formal way of doing that, and we thought, and they did at the time as well, that it would be better if we had some kind of methodology whereby it would basically just say whether something was forecastable or not, or whether it was a high or low demand, without them having to decide what their cut-off points were going to be. So, in terms of the forecastability, and I appreciate that this is a kind of almost circular kind of approach in a sense, is that what we did was we would apply the ETS forecasting method to each of the products' time series, and then we would use the MACE error metric to measure them to determine whether it was forecastable or not. So that where a MACE is less than 1, it indicates that the ETS forecast is less error than the one-step ahead forecasts. Because what you're doing is, where you have the in-sample part, you do the naive forecast, which is basically the next period is the same as the previous period. And it's kind of a standard benchmark for whenever any kind of forecasting method is being developed. Because if your forecasting method doesn't do better than the naive forecast, then it's not particularly much common. So you have the naive forecast, and then you would compare the ETS one-step ahead forecast against that, and then if you're coming up with a measure of less than 1, then that's indicating that it's forecastable. If it's over 1, it's not particularly forecastable because it's producing more errors than the one-step ahead naive forecast. So when it's above 1, it's not particularly forecastable. So there's the formula for doing the scaled error, the MACE there. And then for the higher low demand, we went for a really simple approach. We worked out what the overall average demand of all of their products were to get a feel for what the overall average production level is. And then obviously if an individual product's average demand over a period of time was more than that value, then it's a high production level, and if it was less, then it's a low production level. And that means then that the cut-off isn't decided arbitrarily, it's done by the method itself. So what you end up with is 4 potential choices. So you've got make to stock and make to order in the 2 corners there, and then you have question mark for make to stock or make to order. depending on where it is. So for the makes a stock question mark on, it's got a low average demanding compared to the overall average production level at that time period, but it's also got less than 1 on the makes, so it's fairly predictable in that sense. So if you've got space in your production schedule, then you could put that into it as a make to stock rather than running it on make to order. For the MTO question mark, sometimes some products might initially start off in make to stock, and then over time it might move over into the make to order question mark square, in which case you could probably treat them still as make to stock initially, but then if it's staying over in that quadrant, then it's probably better to start treating it as make to order, because you've got a degree of variability there that's not manageable in that sense. You don't want to end up potentially having an awful lot of stuff on hand in stock, which is basically the idea there. So obviously those products in make to order and make to stock are fairly straightforward to deal with. And then for the other two cohorts, that would be down to the production planner to decide then how to treat them. So the make to stock question mark one is generally the easiest one to deal with. If you've got spare space, plug it in there. If you haven't, then just carry on treating it as make to order. So generally what we found was overall for those products that ended up in the make to order cohort would generally stay as make to order unless they shifted out of that make to stock cohort fairly recently. So things are quite dynamic, so for every review period, in this case it was monthly, the average production level could change because the production levels month to month are shifting around. And then also as well, based on how the time series is behaving, the MACE metric might change as well. So what you can end up happening is a situation where products are moving around the potential spaces that they could end up in. And that way then that kind of reflects the changing nature of a product, rather than just saying, right, we're going to treat this one as make to stock for the next 12 months, and this is make to order for the next 12 months. So you could be changing that on the monthly level. To better reflect how it's behaving in terms of the demands that are coming for it. So that's the kind of dynamic aspect to it in that sense that every review period, things could well change around, and we did find that that was the case. So in terms of the results, what we were doing was I had about 5 years worth of data to play with, so I was able to use 2 years worth of data to establish whether things were forecastable or not, because obviously with 2 years then you are picking up on any seasonal factors and things of that nature as well. So it couldn't be like a year's worth of data because you might well miss any seasonality there. So that worked out quite well for us. And we compared the method against the adapted Soman one that we had initially. So the Dave initially decided the cut-off for the CAV coefficient variation was 0.7, and that anything over 200 was a high production level. That was their initial kind of gut feeling that they were running with there. So we compared both of them. So we do have I did have some results there, and as you can see, the changing numbers of the products in each bucket over time, and that was reflected right the way through the 3 years of the results that we had. And what we found was that the forecastability approach was putting more items into MTS than the adapted Soman method. So it was picking up on those ones a lot more efficiently than the previous method that we were using, that was the adapted one. So I had for the 3 years worth there, and we were picking up on the same kind of things, and products were moving around. Some stayed in the make to stock throughout the full 3 years. Others did shift around, usually between make to stock and make to stock question mark, and they would kind of flitter back and forth generally. And then we had a few that moved across from make to stock to the make to order question mark cohort as well. So they do move around, generally more objects being put into make to stock because of the average overall average production levels. So that for the first year particularly, generally the overall average was sitting at around 240 through to 280, so that was a little bit higher than their initial gut estimate of 200, and so that's how come generally some more products are ending up in that make to stock question mark area. Okay. So we did find that objects in the make to order cohort generally were overshooting the actual demand, and they would have been ordinarily, they could well in the previous method, they were being bumped in the make to stock quite often. So we did find that actually we were getting better results in terms of being able to forecast them out, and then that was helping them to manage their stocks a bit better. Okay, so for future work to go on to this, I do have a data set of some demand data from a pharmaceutical company that I'm going to apply to this just to see how robust it is with some more real world data. And then I'm also going to run a simulation where I'm going to be basically doing a whole range of different products, different kinds of lead times and different review periods as well, just to see how robustly it stands up to being tested. Now, we did get it into the company. But unfortunately, after about 6 months or so, they decided not to run with it anymore, and they went back to how they used to do things because that was what the production planner was more happy with, unfortunately. Which is a shame because I think, to be fair, it would have probably worked for them, but the production planner was quite a stickler for how he liked to do his job, basically, and that was basically where it kind of went a bit awry. But hopefully with this huge work then, if I can demonstrate it's fairly robust across different lead times and things like that, then obviously then it can have application in other areas as well. Okay, so any questions? Hello.
Thank you for talking. Very
Thank you.
interesting.
Okay.
You went in different products moved between each of the 4 quadrants.
Yes.
Is that in any way predictable at all, or is it kind of random? Is it seasonal?
Do you know what? I hadn't actually thought of testing that to see whether I could predict their nature in that regard. But I think, yeah, I will put that in as an additional part, yeah, because that's one way of assessing it, isn't it? So, yes, absolutely. Yeah, so I suppose in that regard that could give you a kind of warning, couldn't it, ahead of time, whether something's likely to shift over from the make to stock to the make to order question mark cohort or something like that. Yeah, absolutely, right, yeah, so that's something that I will add in, yeah, thank you.
So do I understand correctly that product is either an NTO or an MTS?
Yes.
Of course it can change
yes.
over time.
Yes.
But couldn't that be a mix of things where you have a certain kind of a robust stock that you know that you can shift, you make that to stock, and you just top it up with make to order?
Yes, you could do that, and in a way that was kind of what they were having into some of their products were made to stock, but that was at the customer request. But they could well, like you say, I mean, with the products that they know generally stayed in that make to stock cohort, of which there was about, say, a dozen or so that stayed consistently across the 3 years in there, then you know, you could automatically just run that there like that. But the way that they were initially doing it was that they had no clue as to what would be a robust stock in that sense. Yeah, so yes, definitely. But yeah, that could be an approach as well, yeah. Cool.
How did you measure how effective your forecaster was? Did you have a look at like what the inventory is?
Yes, I was checking it against the inventory, and in the run, what we did was that the initial run was done at the same time as they were doing their normal processes, and I would basically compare how that was comparing out with what the actual stocking levels were and see whether it would be better or not. And in general, it was performing that bit better. Yeah, so it was potentially managing their stocks better. Yeah. Hello.
Did you get any feedback beyond that's not the way we usually operate?
Unfortunately not. No. I only kind of heard in the back afterwards that basically they'd stopped using it, and that it was mainly down to the production planner themselves, because they just wanted to carry on doing how they'd done it already. So there was a degree of resistance there right from the outset, to be fair. because they had this concept in their heads already that things just weren't forecastable and they weren't manageable. And I guess in a way, they kind of felt like they were kind of justifying their jobs by constantly firefighting and stuff like that. And it kind of, you know, and but it's a shame because if they were predicting the demand ahead, this would have made life a lot easier for the raw materials. Because some of the lead times on their orders for the raw materials are about like 6 to 8 weeks, depending on where in the world they were getting their raw materials from. So that's way more than the review periods that they were running with. So the purchaser was having to guess most of the time ahead, and they were quite keen on the notion of seeing if things could be forecasted. But then in the other silos, there was the production planning team, and they were particularly awkward, to say the least.
I'm sorry, that must be incredibly frustrating.
It was rather frustrating, and you know, quite disappointing because you put all this work in, and you think you got the buy-in, and then you know you go away and think, yeah, great, I've done something nice and useful, and then 6 months later you hear that you know it's gone out the window. But yeah, so it was a bit frustrating. Yeah. But I got my PhD out of it, so I can't complain.
I wonder whether there might be, I can't quite see what the connection might be, but with problems where you kind of have a base load which would be equivalent of made to stock.
Yes.
And then a top-up.
Yes.
That would be made to order. I'm thinking of things like breakdown services, where
Yes.
the breakdown services will employ a certain number of patrols.
Yes.
And then if demand spikes above
Yes.
that capacity,
Yes.
they'll have contractors.
Yes.
The contractors are more expensive
Yes.
than the guys they employ.
Yes.
So they've got to decide
What that cut-off
what the right
point.
level is.
Yes.
Now, is there some sort of... I mean, the talk about time frames was completely different. Can you respond in a few minutes?
Yeah, right. Months, yes.
Yeah.
Yes. So setting that cut-off point.
Yes, deciding
Between,
how many controls do we need. And
Yes.
With something like breakdowns, because clearly that's sort of seasonal as well.
It is, yes, yeah.
That number may have to...
It would change on a monthly basis, wouldn't it, what that cut-off point's going to be. So in that sense, yes, you could possibly kind of move that over, in a sense, into those circumstances by having the forecast of the expected demand,
yeah,
and then running with that as a kind of cut-off point, or maybe some kind of average over the year or every 3 months or something like that, to back in that seasonal factor. Because obviously there's going to be more breakdowns in the winter months.
Yeah, I think so, yeah.
Something like that, isn't it? So, but then again, in the summer months as well, because there's loads of tourists on the road.
That's right.
So, exactly, yeah. So, they're going to have to be really thinking about that, yeah, absolutely. But that's quite a tricky dynamic problem, isn't it? So, I mean, it could literally be weeks a week in that regard, in terms of managing the finances, because of like the offset from the contractor costs and things like that.
Yeah, and if you've got a severe weather that comes unexpectedly.
Exactly, yeah, you've got all of that, yeah, exactly. But yes, there could well be crossover there, definitely, yeah, brilliant.
So let's thank the speaker again.
Thank you. Okay, let's see if we can plug that in. It should fit, and it's set up to run off. That's good. So, just because it's a Mac, it should still be able to talk, shouldn't it? So, let's see. Oh, yep, there we go. We're up and running.
Fantastic. Well, that worked as well. Great, thanks to all for coming. So I'm going to talk about price forecasting in European power markets, and I'm actually trying to give you an overview of 4 different papers in 20 minutes, which obviously I will fail to do. I'll have to, hopefully at least qualitatively, I will convince you to maybe spend more time looking at these papers and that this is of interest. So, of course, as is the case here, whenever you supervise students, they do the hard work and I get to do the fun bits. And what you don't see here is that a lot of this hard work actually comprise data collection as well, writing web crawlers that scraped data and asking for information from power plants about the physical properties of the power plants under freedom of information, and so on. So huge amount of work without which this couldn't be done. But also we got some data from the quarry, and we had access to their computational facilities, which was much more powerful than what we have at the University of Oxford. So essentially power markets, power is being traded at different time scales. You can start a year ahead, right? You buy blocks of power for say a month, or you commit to delivering for a month, and later on you have another market that kicks in where you say blocks of a week, and then later a day, and so on and so forth. So you can trade that in the forward and futures market for a contract. Money is being exchanged at that point in the futures contract. You can sort of get out of your side of the contract and sell it on someone else. And then there's a spot market, which essentially happens 24 hours before the delivery. Next day, for each half hour, there's a separate auction. People place their bets. Both producers and consumers. And there is a conceptual difference in that these future markets, they are traded in real time. So this is a bit like the stock market. You go in, you say, I offer a certain amount of power for that block at this price, and then a buyer comes and buys it. And as trades happen, the price moves up and down. But the day-ahead auction can't function in this way, because it has to then guarantee at that point that the power that's being traded is also deliverable, as in that you can actually take it through the grid without exceeding the loads. And this is not a planning exercise as such. It's not like pumping gas down some pipes, because electrons will find their own way, right, according to Kirchhoff's law. So it actually just depends on how much power you inject and extract at different points, and the bids that are accepted have to satisfy it. And that's why it's done in a closed auction. So you place your bids, and then this auction has to be cleared. There's a little bit that's done kind of intraday, but that's a minor part of the market. And so the literature on predicting or forecasting electricity prices basically can be divided into non-structural approaches that just kind of use mathematical finance type of approaches to predict the stochastic behavior of prices, and then structural approaches that started with the stack model and then moved on to game theoretic approaches, which is where our papers contribute, and that's more like a digital twin of the market, if you will. So you're trying to predict or forecast all the market actors and what their bids will be and what the network constraints will be, and then you carry out the market clearing, and on that basis you come up with a predicted price. So here is an example of a structured approach. This stack model essentially says like you have different types of power plants with different types of fuels, and so they sell power therefore at different costs, so therefore they come in at different price points. And so if you know the total demand, then you need to go into this cumulative volume. You need to match that volume, and then out comes the price. And so then everyone gets that maximum price. So all the contributors, power providers bid at their marginal prices, but they may get, and they hope, a higher price. So they bid at their marginal price so that they never have to sell power at a lower price than what it costs them, but they hope that the price will be higher and then they make a net profit. And so if you look at, so why is this important? It's because if you look over the long term, these power prices are very spiky. So sometimes you have days where, so the average price per megawatt hour is around £50, right? That's the wholesale price. Of course, as an end user, you pay a lot more, but that's because you pay for the grid use as well. But then there are moments where basically this quadruples or quintuples, and you as an end user end up still paying your guaranteed price, and it's your wholesaler that has to absorb this price. So these math finance approaches that just kind of analyze the distribution of these spikes and the severity of the spikes, they can be used to ensure that the wholesalers remain solvent, right? As a kind of insurance, an actuarial approach. But what we want to do is we want to kind of look at the finer-grained detail of these spikes and predict when these spikes are happening. That usually is also the case when you're close to a blackout because there's not enough standing reserve in the system. And so here you see a few consecutive days, and it's maybe not surprising that you have kind of a peak at midday, but these peaks can be quite different from day to day, and so can you actually predict this? So I'm now going to first talk about future markets, our game theory model for the futures market. So here we don't have to take network constraints into consideration because they're kind of out of the picture. The idea is that in this market, the wholesalers cover themselves with kind of baseload demand, and so when we talk about producers, right, these are usually power plant operators or companies that own multiple power plants, and they might have power plants of different types. So they need to buy fuels and carbon emission certificates, and they sell this to consumers, but these consumers are really the wholesalers. These are the companies from whom you are buying your power, and they sell it on to the end users. So whenever I refer to consumers, these are actually the wholesalers. It might be that a company is both a producer and a consumer, but they're still that's not always the case. And so from a producer perspective, you plan to deliver a certain volume of power into the grid at a specific half-hour slot. 1 year or several months into the future, or several weeks into the future, but you can buy your fuels at different times leading up to that, and you can trade your commitments at different points into the future. There's several trading points along the way until the delivery date. So that's why inherently this game, as you set it up, actually has to consider all the trading points along the way, which we discretize to get a finite number of points. But inherently, you get not just the price of the end point, the kind of spot price, but you get the whole term structure of the price. So you might think that, obviously, surely this price must be a martingale, and so therefore that must be, if you look in the average flat, but this is not a martingale because it's a perishable good. So this half-hour slot will expire, and then beyond that, it's gone, and if you haven't delivered, the opportunity is gone. So it's not a martingale, and that's why, even in expectation, these term structures are not flat. Another consideration is that if I buy all my fuels now, then I know what the price is. I buy these in the wholesale markets. If I delay buying these fuels, I might get a cheaper price, but I'm running the risk. So there's risk that I'm taking on, and in all of these considerations, there's this risk of delaying decisions that you have to take into account. So I'll show you a bunch of slides that are kind of maybe very heavy on notation, and so you don't have to worry too much about that. Details are in the papers, but the point here is that you need to discount all of these. So if you think of the profit that a producer has, then you do a net present value calculation, discounting all these payment streams. And you essentially just take the price, right, that you agree at a specific time, TI, for delivering delivery period, capital TJ, times the volume that you trade minus transaction costs, right, and the fuel costs and the carbon emission costs. This is essentially what it is. But then, of course, where it gets complicated is you have constraints, right? So the total volume of power that you sell, summed over all the trading periods, must be equal to the volume of power that you actually deliver at the delivery time TJ. And then you need to have enough fuels, right, to be able to, or accumulate enough fuels, which you buy at different times as well, to be able to deliver. And at that point you need to know this heat capacity C, right, of your power plant. You need to know what the physical property of the power plant is, and you need to know how much carbon emissions it generates. So there's another parameter G there, and this is where literally it took months to gather all this information, because there are 400 power plants, and the order 400 power plants in the UK in this in this work. We determined these coefficients for 400 power plants, and then there's the issue, a further complication, that if you plan the delivery into a half-an-hour slot, then that's coupled with what the delivery in the next half-hour slot is, because power plant can't be ramped up, or can't ramp up or ramp down production at arbitrary speed. So again, every power plant has its own upper and lower bounds on the ramping speed, and you need to find out what these are, right, for each power plant. So you need these physical characteristics, and then the stable output limits. So there's clearly an upper bound on how much power a power plant can deliver, but there's also a lower bound below which it's just not economical to run. And this then introduces basically binary variables, because you either deliver at least this much power or you don't deliver at all. So that then introduces kind of big N type constraints. Right, then to model the risk averseness to uncertainty as we go into the future, we have modeled this in the original work with Miha through a variance of all these. So VP is not just the volumes that you trade, but it's basically all the decision variables stacked. We later generalized this in work with Julien to other risk measures, and also taking into account that as far as demand is concerned, it's actually the opposite. So for prices, you have uncertainty that grows into the future. You know exactly if you buy your fuels now how much you will pay, but you don't know what you pay in 2 weeks. When it comes to demand that will occur in a specific delivery period, is the opposite. You have weather forecasts maybe, or seasonal forecasts, and then as you get closer and closer, your forecasts become more and more precise. So your uncertainty decreases in this direction, and That's how Julien's work channelized this. But essentially, each producer solves if you will here, a mean variance optimization problem under this model, where we work with, so given the expected prices, we knew the term structure of all the prices. So that's part of the input here, but of course, actually it is part of the parameters that we want to come out of our optimization problem. You'll see how that's done. So consumers solve a similar problem, but they have other variables. I don't want to go into these details. The point is then that at the end we have one constraint that ties everything together, and that's that market clearing happens at a competitive equilibrium. That is to say that if every participant in the market plans ahead how much fuel they're going to buy at a particular time, how much they trade in the futures market, and so on, and we call it a strategy. They want their strategy to be best in a game theoretic point of view, from the point of view that if everyone else has their strategy and they can guess what their strategies are, then they don't have an incentive to change their strategy. So it's a Nash equilibrium in that sense. But also we have that the total volumes that are traded on the producer side and consumer side, they have to match up. And so, whereas I can solve for the trading strategy for each producer or consumer given the expected the term structure of the prices, I now need to also adjust this term structure, all these prices, in such a way that the volumes that come out of these optimal strategies match up in this sense, that the market clearing constraints is satisfied. So that's why it is kind of a bi-level optimization problem, where in an inner level, given the prices, you can solve for these volumes, and then you need to adjust. In an outer level, you need to adjust the term structures until everything matches up. So, it may seem trivial, right? Mean variance optimization, we can do that, but the problem is that we have binarity constraints through these stable output limits, and I will show you on the next slide that actually it really matters that you take those into account. And so that immediately turns this into a QP with binarity constraints. And then the other thing is that because of the coupling of different delivery slots, you end up with a gigantic problem. So here, we just create a forecast over these 4 days essentially, and we need to forecast for each half-hour slot in these 4 days. We need to forecast what the term structure is. Then we end up with on the order of 1 million decision variables. So it's a gigantic problem. And so there are some parameters we need to calibrate, and just to show that actually these term structures, they will actually vary as a function of these of the parameters there. So in the interest of time, I move on. But I think I want to show you this slide here, that if you now forecast the prices on over a period of 4 days, right, but 2 months ahead, we forecast that, then we see the dashed line there is the actual price on these days, and the black line is our forecast. So the first model takes ramping constraints and the market clearing constraints and load balancing and all that into account, but not the stable output limit, this lower stable output limit. And so it fails to capture these spikes, right? I mean, kind of the seasonality is right, but it fails to capture these spikes. If we now take them into account, and immediately that means that we have binarity constraints in our problem. How do we solve that? We identified a series of simpler IP problems that were totally unimodular, so we can actually solve them very quickly. So this is an approximation of the actual problem we want to solve, but then we do capture these spikes, but in a kind of an exaggerated way. And then in the final model, we took into account that the grid operator is also putting penalties into place, whereas every market participant has to pay a little bit of a tax for the grid operator, then pay sort of some gas power plants to be on standby, just in case they're needed to kind of cover one of these peak periods. When you take that into the model, we get pretty close to the actual price. Okay, so I realize that I am failing in giving an oversight of four papers, but maybe I can give you a little idea of what we did with Alex. So here we looked at a day-ahead auction in the European power markets, and that's when the network constraints come into account. And so the European Power Exchange has this peculiar rule that is politically driven, that you divide this area up into different zones, regions, usually countries, and then you want the price that comes out of the auction to be the same throughout that region. Now, in the North American markets, they don't have that rule, so you have at every point, every node of this network, you might have a different price, and that actually ends up being an easier problem to solve. But for political reasons, in Europe, they want the same price in, say, over a whole country. So at that point of the day-ahead auction, you start trading. Maybe you have excess capacity in France, right? They have the nuclear power plants on, and they know maybe a demand forecast for France. They know that they have excess capacity. They can start selling into Germany or into Belgium. So they can bid for selling power across the border, and this will obviously create power flows that then need to overall satisfy the network, the physical constraints of the network. So the power exchange actually does a very simplified thing. It needs to, first of all, it can't actually predict, or it can't walk this order book, clear the book in such a way to really ensure that the physical deliverability is guaranteed. But what it can do is it can predict kind of a base scenario, right? And which it can guess the outcomes of the futures market. We have now completed at that point, and they can say, well, on that basis, and we have a forecast for the demand, who in these different zones is going to inject additional power, and where will it be extracted? And then basically their scenarios are just, in which proportion is additional power being injected and extracted, and then they linearize the entire impact onto the system around that scenario. So essentially, they take you have huge dimensional space, right? have one line and you take a directional derivative in the direction of that scenario. And then the question is, how much can you actually scale up this scenario, or the base load, the base scenario plus multiplier times that vector before you start exceeding the power load, the allowed power load on one of the lines. And then they produce maybe multiple, yeah?
Like 2 minutes left.
Sure, yeah, exactly, thanks. So if you amalgamate all these constraints, and then it ends up being linear constraints on the decisions taken by all the market actors, but these constraints, whilst taking them into account during the market clearing, they only publish a very small number of these constraints, the most constraining, if you will. So the market participants don't have full transparency over what the auction is, how the auction will be cleared, right? So you would think that you would want to have full transparency over who gets precedence over whom in clearing this market. But actually, you have only very limited information. But of course, if you can actually predict what the full set of constraints is, and you can forecast what the bids will be of the different participants, then you can simulate the whole the whole auction and what the outcome is. So I know that I have already gone over time, so I'm going to have to skip all of this, but just to show you that I mean, these are some numerical results. You can see that each of these double peak periods is 1 day, and then so we have the target cost is the actual price that came out of the auction, and the blue cost is what we forecast 24 hours ahead, and then of course this is a kind of a moving window that's to cover all these days. The exciting part of our paper is that we then have a new way of clearing the market that would give you lower prices, and that's this Model CM truthful bid there that you can see that would actually lower the cost for consumers. But I'm out of time. I'm giving you the references for the papers if you are interested, and then also, of course, there's a lot of other literature on this that you give credit to as well. So we probably have time for 1 minute time for a question or two. Yes?
You mentioned your simulations scale are quite large. What type of resources are you needing to do this simulation?
The first one, on the futures market, or on the second one? Because so the first one we actually ran on a cluster at the Mathematical Institute of University of Oxford. So it is feasible on, and that was in 2013. So some of the simulations I showed you in 2013. This was very challenging, but today this would be quite easy to do. The later bits, these simulations here, they run in a specific cloud called Descartes. And so it's basically Macquarie that paid for that access. Is not something that I could do on my laptop. Yeah.
So is it been taken up by actors in the markets to the events of kind of guesstimate better?
So Alex now works at a power trading hedge fund.
I'm surprised, yeah.
Miha has his own power trading hedge fund.
Of course.
Of course. Macquarie are still, I think, trying to figure out what we have done.
Okay.
Yeah, I mean, what we actually hope is that we can influence policy, right, with this new way of clearing the market, because there is considerable, anger, I guess, in the people read in the FT that everyone always pays the highest price, right? And if you have to go to the limits of the system, then it's always the most expensive power plants that will be switched on. If you think of that stack model, and then everyone pays these highest prices all the time.
Sorry to interrupt.
Yeah.
Is the third speaker present?
It's not that. It's not here.
It's not here.
No.
Brilliant.
So,
in the game theoretic part, what's the sort of information structure there? Do the participants have common information, or do they just have partial information about their own situation?
But you'd hope they have information about their own situation. I mean, so we had to make, obviously, you can see that the blue price doesn't match the red price exactly, so we had to make some assumptions. And the assumption that we had to make is that there's a specific form of the marginal cost. So if you say ask someone to inject more power, then this will be more costly because it kind of uses their resources more. Maybe they need to buy in energy input from more expensive sources and so on. So the assumption there was that this is a affine function, so that's a big assumption.
Yeah.
And then you've got these parameters, MI, AI, which you need to then calibrate for each type of power plant, right? And because different countries have different mixes of power plants, and so from that you can then kind of estimate what the stack model will be for each of these countries, right? And then you can start thinking about how they will. So you need to predict the actions of everyone in this auction. So it's a big ask.
Yeah.
And maybe you might think that it's totally hopeless, but this shows that it's not. It isn't totally hopeless because when you I don't know. So here you might think that all of this is surely just predicted by by the gas price, right, or something like that. So we plotted the gas price down there, and then this does fluctuate as well. This also has the same seasonality, but it isn't the only explanatory variable, and so this the output from our model gives you a much better prediction, much better forecast than if you just scaled the gas price somehow.
Another question for you.
Sure.
Back in 2013, you had a lot of coal and gas plants. The energy generation mix looks quite a lot.
Yeah, exactly. That's why this is kind of dated experiment, but that's still.
Does most of it carry over?
No, but the point that I was making earlier about predicting that the idea that the demand itself becomes more uncertain as you go towards the delivery period. The same is true for renewables production. And renewables will then just pretty much inject that power. So you have a kind of a base load that will come in, but that is in itself unpredictable. Well, it's not completely unpredictable, but you have more uncertainty the further back you are, right? So as you go forward, that certainty grows, But as far as prices are concerned, the uncertainty grows, and so this is why we have that extension that Julian's working on. Yes.
So this could be used just to model the base load, everything except for renewables. Is that right?
No, that's not quite true. I just didn't. Julien didn't have up-to-date information about the physical properties of these power plants. So when I go back to Mihal's model, so he got these heat capacities, for example, for each of the power plants, right? Which was in itself a huge data gathering exercise. So Julien didn't have that up to date. So Julien worked much later, right? So Mihal's work was in 2013. So that was sort of out of date as well. So we couldn't then repeat a calculation like this.
But not just because of missing data, but also because like this whole idea of fuel doesn't really translate to renewables, or I'm not sure.
It does translate, because what you can do is essentially, if you say this renewable production will be injected into the grid, unless of course it leads to an overload somewhere, but it basically just takes away from the demand. So you can actually factor that into the demand. So there's another uncertain. So demand becomes more uncertain.
So you bring it on the right-hand side of the.
Yeah, exactly. Yeah. So in 2013, when we did this, obviously the demand for the UK was quite predictable, because if it gets very cold, people switch on the heating and so on. So weather is a factor, but then you have mainly factories and so you know what time it gets dark and so on. But if you we also looked at Brazil, and so that's far less predictable, because everyone has set their air conditioners at a thermostat. And then when the temperature goes above a certain threshold, suddenly everything kicks in, and then you have these kind of jumps, these huge jumps.
Brilliant.
Good. Well, thanks very much for coming and for the discussion.